Hi, in this video, we want to take a look at unidimensional dichotomous models for item response theory. Okay, so what we've got going on is that we have, let's say, standardized tests, and we're looking at the situation where it's either a 0 or a 1, typically a multiple choice situation. So we've got a bunch of students, we have a bunch of questions, which we'll refer to as items, and we'll refer to the students as persons. And we want a statistical model to give us insight into the questions, into the students. And we want to know more, we want to go a little bit deeper into the test data than just, the scores and average and stuff like that. Okay, so what we're going to do, we're going to create like a Latin trait model for each individual student. And that's going to be kind of like our understanding of the student's individual ability. Now, something about this is that this does a better job of taking into account aspects of the questions. So if I was just to take into account like the overall average score, the overall number correct, yes, this gives me that type of information, but it doesn't take into account question difficulty or the ability to guess on a question or a question's ability to discriminate between proficient students and non-proficient students. So what we want to do, we want to get more going. We want more inference off of our standardized tests. Okay, so first one we're going to look at is a rash model. So the rash model is going to have, there's going to be two parameters involved. Each question gets an easiness parameter, and each person gets an ability parameter. And these two together go into a logistic regression equation, logistic regression curve to model the probability of getting a particular question right. So there is a question aspect and a person aspect. So it accounts for the difficulty or the easiness of the question and accounts for the individual's ability. Okay. Now, how we approach this, how we word this in terms of more sophisticated statistics is that a rash model is a mixed effects logistics regression model with items as fixed effects and persons as random effects. So we're treating the difficulty of each question as a fixed effect, and we're treating the overall ability of a student as the random effects in the model. The random intercepts correspond to the person parameters and the fixed effects parameters. Or the fixed effects parameters are the item location parameters. So what this item location aspect, what's going on here is that we're modeling that every single question, the probability of being correct is a curve. And it's the same shaped curve, but it shifts left and right depending on the student's ability. So, or depending on the difficulty of the question. So if it's a very, very hard question, it's going to shift far to the right. If it's a very easy question, it's going to shift far to the left. And the student's overall ability indicates the likelihood that they would get it correct. So we're going to go ahead and use some data, and we're going to use a Zariski data set for this one, which is in the MPsychoR package. But we're just going to look at subtraction. And why we're only looking at subtraction is just to keep it a more concise example so that we can emphasize other things that we want to look at right now. If I was doing a full project, I would definitely be going into more columns than just subtraction. Okay, so something about the rash model. If I look under the hood how things are actually computed, the difficulty of the first question is not actually computed on the first run. So that's going to be treated as a reference level. And then all of the difficulties, the easiness parameters for the other questions are computed. Then after all those are done, because the first one is a reference, we go ahead and say, okay, we want all the coefficients to add up to 0. Okay, so then we go back and we set the difficulty parameter of the first question as whatever it would take to add up to 0. Now, something about difficulty and easiness. So the difficulty is the negative of the easiness. Now, how is presented in the ERM package in R, estimate the rash model, ERM, is that is an easiness parameter. And by multiplying by a negative sign, it turns into a difficulty parameter. So when you hear me say easiness or difficulty, I'm really saying the same thing. I prefer saying difficulty because I think that gives a better, I think it reflects what's going on with how we think about questions more than saying easiness. All right, now there are some assumptions for a rash model. First and foremost, we have unidimensionality of a latent trait. Okay, this means that the results of a student's score come from one factor, one hidden latent variable that we cannot directly observe. That we're making the assumption that there's one, not two, not three, not four. We have parallel characteristic curves. All right, this is saying that each of the, if I graph the logistic regression equations that come out for each individual question, they're going to have the same curve. They're just going to be left and right shifts of each other. And the amount of shift comes from the difficulty. Now, the logistic regression curve with respect to that one latent variable has slope 1. This is a big one. And so not only do they all have the same slope in terms of logistic regression, it's slope 1 for each of them. And furthermore, we have local independence. All right, so by local independence, what I'm saying is that all of the difficulty parameters and all of the latent variable estimates, these are independent of each other. Okay, so now if I think about the unidimensionality of the latent trait, because of how it's computed, we're not making an assumption that there's independence there. We're not making assumptions about the difficulty parameter because those add up to 0. But we're saying that the ability parameter and the difficulty parameter, the estimates are independent of each other. Now, the local independence one, that can be kind of hard to actually evaluate. There are some things inside the ERM package that enables us to do it, specifically NP tests, non-parametric tests. And what it does, it doesn't check independence, it checks for dependence for us. And it's not quite what we're looking for, but it's what we've got, and we'll go ahead and use it. My understanding is from looking through the textbook is that much of the literature, people using this, they usually don't actually check this. Now, the default method in ERM, a fitting a race model, is conditional maximum likelihood, which is very standard. All right, so when I want to go through, I want to fit the model, I'm going to go to the ERM package, and I'm going to go RM for race model. Boom, we got it. And I can fit a few other parameters. And now if I do coefficient, I can look and see what are all of the easiness parameters. Now here, these are all presented as the easiness for us. If I want difficulty, just take a negative sign. Okay, so how this was actually computed was that these values were computed first, then the system went back and said, hey, what does it take to have these add up to 0? Boom, there it is. Okay. And so I can see like which question is the hardest. Now, another way I could look at this, of course, I could look at the average score for each question, right, across the students. That will give me similar information, but this actually, this gives it probably a better representation because here, this difficulty is actually taking into account the student's ability. Now, the student's ability, something that's interesting about this is that if there's a really hard question and a student misses it, then their score isn't going to bump down very much. But if it's a very hard question and they get it right, you can see their ability parameters go up quite a bit. Conversely, if a question is very, very easy and they get it right, there's not going to be much change in their ability parameter. But if they get it wrong, you'll see it drop down. There's a constant back and forth on this. And of course, we can get confidence intervals. And so if I see 0, that means that it's relatively like center compared to the rest of the others. So it would be towards the middle of all of the curves when I look at the curves. Because remember, they always add up to 0. And so we have positive, positive, negative, negative. Here we have a sign change. So remember number 5, negative, negative, and here is a sign change. And we can go in and we can go ahead and run summary. So we'll get the conditional log likelihood, number of iterations. So remember, if I have a good model, it usually doesn't take very long, a large number of iterations to have it converge. If it takes a long time to converge, that's a sign I have a bad model structure for my data. Here, 12 is super low, so I'm happy. And here are the number of parameters. Now you'll notice 2, 3, 4, 5, 6, 7, 8, but I'm missing a 1. Why is that? Well, the 1 is the reference level, so we're not getting a confidence interval off of that. We do get an item easiness though. So this is the difficulty parameters and item easiness. And there are different interpretations for this. They are related to each other. If you look at the equations, you can see like how they correspond. All right, so now let's go ahead and do some plotting. All right, so here we're plotting each and every one of the curves. Now you'll notice that this S shape is the same as this S shape, which is the same as this S shape, which is the same as this S shape. The only difference is that they're shifts of each other. Now, which one is in the middle? Well, we saw that 5 and 8 had 0 inside their confidence interval. So we're looking for those to be somewhere in the middle. If I go 1, 2, 3, 4, 5, 6, 7, 8, we can see 5 and 8 are actually the 2 in the middle. All right, well, that's reassuring. Now we can plot each individual of these curves if we want. I don't feel that this is very informative. I feel like the one with all of them lets me see more. That way I can compare what's going on. So we can see that these two curves, 7 and 3, are very close to each other, while 1 is very far from it. So 1 is the easiest question. You'll notice that it takes the lowest ability to get like the greatest probability, while 3 is the hardest question. It takes a much larger ability. So if the student has like an ability of 4 for the latent variable, they still don't have nearly 100% likelihood of getting it correct. While over here, if for question 1, we can see if the student has a latent ability of 2, then they are very close to being guaranteed to getting the question right. Here are the individual curves by themselves. And here we once again look at our difficulty parameters in terms of the estimate and the standard error. Now our model matrix, this gives us insight into how things were actually constructed. And it's the main reason why I'm showing you this is that we can see that number 1, question number 1 is the reference level, because you can see that -1's all the way across. Now the person parameters, this gives us an estimate of, it actually gives us more than this, but I'm only showing the initial output. If we use the str function, we can look at the structure and get some more stuff out of it. But we're able to just look at if a student gets a 0 on their raw score, this gives us an idea immediately of what their under the hood latent variable is for ability. If they got 5, we see that's about 0.64. So we can see that students that are around 4 or 5 is about average, and students doing better than 5 are doing better than average. Students doing worse than 4 are worse than average. And you'll notice the extreme values do not have standard errors, and that comes from the fact because they're so extreme, so far out, that fitting on when you have all 0s or all 1s on a row is not it's not algebraically the same. And we can take a look at our variance covariance matrix. between the estimates of the easiness. And now let's go ahead and take a look at the overall rash model fit. So first thing that we can look at is the log likelihood. So the larger the value, the better for this, because we want to maximize the likelihood, but we're working on the log scale. So that way it's if I get like super small values, it's really hard to evaluate something. When I have higher dimensional probability distributions that I'm assuming are in play, when I do my likelihood, I can get very small values. I take logarithms to deal with it. Log of anything less than 1 is always negative. So therefore, we see what we've got. Now we can do ANOVA also, and you'll notice that it's giving deviance. So here's the conditional likelihood that we looked at before. Here's the deviance. So it's not actually ANOVA that's being ran. This is taking advantage of chi-squared. All right, so now let's go ahead and do some hypothesis testing. So I have my score, and I also have how long it took. Now with the students that with their time, I've got faster students, I've got slower students. What if I was to group the test results by fast and slow? Can I see differences in scores? Okay, if I see that there are differences in scores, then really what I've got going on is not fully capturing everything, because I have an outside variable that I can identify traits with. Okay, so what we're going to do, we're going to create a new vector of did the student do better than average on speed? Were they faster than average or slower than average? And so we're just going to say, are they greater than or less than or equal to the median time of all the students? And then what we're going to do, we're going to do a likelihood ratio test, and I'm going to split the two groups up. So I've got the fast students and the slow students. And now I'm going to take a look at the theta parameters for the two groups. This is similar to a two-group t-test. Okay, well, we have a likelihood ratio value of 24 and chi-squared degrees of freedom of 7. All right, so if you think about that for a moment, we get a small p-value. All right, we just remember the expected value is going to be around like maybe 14. And so it's kind of a deviation from that. All right, so what this says is that I have another variable outside of my data where I can identify the two groups, and there is a statistical significance between the data and this outside variable. All right, this means that my model has some problems with it. All right, so let's go ahead and do a wall test on the individual easiness difficulty parameters. And here I've got my z statistic, and here I've got my p-values. And if I look through, we can see that number 3, number 5 are statistically significant. Okay, so here I'm going to be I'm going to start digging in. Specifically, I'm going to be looking at number 5. So what I'm going to do, I'm going to do a graphical model check. I'm going to do a plot for the beta for the group for the fast students. So if I was to rerun the model and I looked at the beta values for the fast students and I looked at the beta values for the slow students as the difficulty parameters, and then I take a look, assuming that we have a bivariate normality to make these ellipse, I can get this plot right here, using some confidence interval, or it's not confidence ellipse actually. And I notice that things kind of go along this horn shape, the confidence interval, but I notice number 5 is sticking out. It's completely outside of this confidence interval shape. Okay, so I suspect that there might be a problem with number 5. It might be evaluating something very different than the rest of the test. It might be a poorly written question. It might be that half the class just cheated and knew that one question. I don't know. I just know that there's a problem. So what I'm going to do, I'm going to take a look at backwards elimination. So remember, I had a few that was kind of like, hey, remember 5 and 3? I'm not 100% sure about both of them. Now, remember, when I go through, anytime I'm doing statistical modeling, I want to remove one variable at a time, rerun the model, and then evaluate. And if I want to remove again, I remove one at a time until I'm satisfied. So what we're going to do, we're going to do stepwise backwards elimination. So this algorithm will go through, it will find the difficulty parameter that would be the best to remove it, and then check to see is that an improvement or not. If it's not an improvement, then they're not going to take it out. Okay, so what it does, and this is going to repeat itself over and over and over until it's satisfied with the model. We see that it only removes one item. It removes number 5. And then when I look at the stepwise elimination hypothesis test, we can see that there's a statistical difference between this model and the full model. Okay, so now what I want to do, I want to rebuild the model, but without the 5th question. So I'm removing the 5th question from my data set. I'm just dropping it into ratio model in the ERM package, and I get my coefficients. All right, so let's take a look at number 3. So negative 1.7 here. I go back up. Number 3, negative 1.68. All right, so it shifted a little bit, but not too far off. If you see values change a lot, that's a sign that you have colinearity in your data. I have to find where I was. All right, here we are. All right, so now let's go ahead and plot the graphs. And things are similar to how they were before, okay, except we're missing number 5. Let's do a likelihood ratio test. Now my p-value is not statistically significant. So this indicates I have a better fitting model. And so now I'm satisfied with this model. So now I want to check for local dependence via a nonparametric test. So I'm going to use NP test, and I'm going to set method to T1. Now, it's not obvious what T1 means. If you look in the help documentation, it has a whole list of different methods to use for different tests. There are a lot of tests available. Here, we're just going to look for local dependence in this one manner. And so we're just going to do 1,000 iterations because this is a non-parametric method. I believe it's doing a bootstrap iteration. And items, pairs with one-sided p-value less than 0.05, none. All right, so that is reassuring that we don't have any issues. Now for a global test for dependence, I run the same thing, but now I go T11. And this statistic calculates the sum of absolute deviations between the observed inter-item correlation and the expected correlations. And we see that we failed to reject the null hypothesis. Okay. All right, so now what I want to do, I want to see in my data set, I have a record of which class each student was in. So I want to see, are there different abilities within each class? Now, this could be from teachers. This could be from like students, like the stronger students being in one class, weaker students being in another. It could be another factor that we don't know. We're just running it and seeing, does it look like there's a difference somewhere? And how we do that is I get the person parameter, I get the theta, notice I get the theta dot table, I get the ability parameter for each individual student, and then I tack it onto my data sets. Now what I'm going to do, I'm going to do analysis of variance with theta depending on the class. Theta is numeric, class is categorical, and then I just run AOV. And we can see that we reject the null hypothesis. We conclude that there are differences between the groups. Well, so this means that we believe that one class is substantially weaker than another class. Now, why that is, we don't know. We have to dig into the data with subject matter knowledge, which we don't have, but we would know what to do at this point. Now, let's move on to two-parameter logistic models. In this situation, what we want to do, we want to allow for different slopes for each question in terms of the ability parameter, that theta that we looked at a moment ago. All right, so this adds another level of flexibility, another level of complexity. So when we do this, we want to make sure that we have enough data. Anytime I want to add on a parameter to a model, I want to make sure that I have sufficient data, that I'm not doing, I have a good number of data points per parameter in my model. Otherwise, don't do it. Go simpler. And this parameter, the slope for the ability, is called the discrimination parameter, and it'll be for each question. So now I've got a slope for each question, and I have an intercept, which is the difficulty. So discrimination is slope, and then difficulty is like the intercept in terms of the logistic regression presentation of the model. All right, now when I do this, unless something weird happens, the slopes will not be parallel to each other. Okay, so if that's important to you, that's something that you need to take a look at. Why would parallel slopes be important? Well, if I want to be guaranteed that a harder question, I want to be guaranteed that if I have two questions and one is considered harder, then the student with the better ability factor will get the better probability. If I want to make sure that the better ability student gets the better probability, then I have to have parallel lines. If I don't, I can get a little bit of wonkiness, usually at the extreme ends of what's going on. Most of the time, like for my personal modeling at work, I don't worry about it. But if this is an issue, you just go up to the Rasch model. All right, algebraically, the log odds ratio is equal to the slope times the change in the latent variable. All right, so the slope, this discrimination, shows how much a person needs to increase their latent variable, or how much they have to increase the latent variable to change from 0 to 1 in terms of a probability statement. So now, something that is in the literature is that a good, quotations, discrimination parameter are typically between 0.8 and 2.5. Outside the range, either the curve will be super flat or be super steep. So if I have a very, very large value, then it's going to be a very steep slope right around that probability 1/2 mark. And so it'll be like a light bulb in terms of getting it. Either they get it or they don't. There is no gradient in the middle. Now, if it's a very, very small number, then it's going to be a very shallow curve. It's not going to be increasing very quickly anywhere. And that means that it would take a lot of improvement on ability to get a substantial increase in the probability of being correct. All right, so now let's go ahead and get some data. Let's take the RWDQ, so work design questionnaire. And we're going to fit a two-parameter logistic model. Now, here we need unidimensionality of the latent traits. So we believe that there's only one factor driving the results, but we still need independence. We don't have the restriction on the slope. We don't have restriction of parallel lines. Now, for this package, we actually have to be able to use the functions, some of the functions that are in this example, we have to actually load the library. I prefer to not load packages, but whatever, I don't have a choice on this one. Now, when I do this, when I build the model, you'll notice I say that my entire data set of zeros and ones depends on a latent variable. Z1 is latent variable 1, Z2 is latent variable 2. And this function will allow us to use both of those. So I could have Z1 plus Z2, or I could have Z1 with an interaction with Z2. Either way. And here we get our difficulty and our the discrimination parameters. So this is slope and this is intercept in terms of the link function of logistic regression. We are log likelihood. Now, if we go in and we start looking through, just like we did with the previous, number 5 question, we'll notice that number 22 is substantially different from the rest. All right, so from analysis of what was going on that, not part of this presentation, it leads us to believe that 22 should be removed from the data set. It's inconsistent with the rest of the questions. So now I'm going to go through, remove that column, rerun the model, and we get our results. And now we can look at the item fit. And if I go through and I look at this, I notice that all of my p-values are greater than 0.05. Now here, number 34 is kind of close, but this indicates that we don't have any problems with fitting for any of the individual questions. So I'm feeling pretty good about this model. Now let's go ahead and plot the curves. Now you'll notice that this S is more steep than this S. So you can see the one that's steeper here, this darker green, is steeper than the light green. All right, these are non-parallel curves. So you see that they're not just translations of each other's, they actually have different shapes. And you'll notice that over here, if I have 2 students with like low ability, and we can see that there's kind of an inconsistency in where students would land in relation to each question given their overall ability. Some people won't like this. Some people have a problem with it. For my work, it's never been an issue. And we can get further information using the factor scores. Now, the next one we want to consider is student guessing. So here we're going to do a 3-parameter logistic model. It's going to be the same model as we had before, but we're going to tack on a parameter for a student's ability to guess. Okay? Now, something I did was I took a look, I fit the model, I took a look at the output, and I noticed that it took a kind of a little bit of time for it to actually converge to get to the final values. So I went ahead and I looked at each of the columns of the output, and I took the column means as the initial values for the initial guess, the starting values for the algorithm before it started iterating. And I did this just to speed things up. If I was actually working on a project, I would not have included this unless I had actual prior knowledge. Doing this just speeds things up, and so that it's in the ballpark of the values I want it to be in. So here, the starting value for guessing was 0.2. The initial starting value for difficulty was 0.7 for all of these, and the initial discrimination starting value was 1.7. And we can see that these values aren't too far off from what I have here as a data frame. Now, the values did change with not having starting values and having starting values. So that might be an issue. I would want to like dig in, but it didn't change much, so I'm not too worried about it. All right, and now I can plot the curves. Now, once again, we see the S-shaped curves, going all the way up to 1. And we can see that we have different shaped S's. We have different steepness. Now, the difference is really on the left. So here, if I look at this curve, student guessing, that if students were just purely guessing and not doing anything else, they have about a 0.4 chance of getting this question correct. 0.4. Well, like here, they would have probably, let's say, a 0.05 chance of guessing if they were guessing randomly. All right, so this gives me insight into there might be something about my questions that are enabling students to get around actually solving the problem. And if, like they're able to, let's say they're able to eliminate, all but two of the possibilities on a multiple choice test because those other possibilities are clearly wrong, then I'm really not assessing the student's mastery if there's really only two options. All right, well, that's all I've got for you. Take care and goodbye.